day we're doing this. So we're taking images, for instance, here, and making it smaller in this direction. There is a compression in this direction. So let's say that we have an image. Let's say that it is defined in a continuous grid. And then let's make this it's not continuous, it is just vamos aquí, era era sobre scale. Okay, so we have an image that is defined in this grid. We want to make it smaller, and we want to produce an image that can be by time. It's also defined on a discrete. And there is a relationship between coordinates into this space and coordinates in this space. The relationship is this one. Put in there is a contraction of x, contraction of y. Right. Okay, so this is our relationship. So you take an x and y coordinate from these, x prime and y prime, you multiply by a matrix, and then you have the coordinate in the original space. But there is a problem. This coordinate, probably, it is not an integer coordinate. So you have to approximate it to some location that you know, and this location that we know. So you have to make it integer. And what we saw the other day was this rounding, and rounding is nearest neighbor separation. That means, so let's say that here we have our tree, and our location is here. So when we make the correspondence, we make this multiplication together, we end up in this location, and then we don't know the image at that location. We know the corners. What we have to do is to round it. So by rounding, you are shifting the coordinate to this location. That this you know then how much is the image at that location. So you do this interpolation, and it is because you are moving to the nearest neighbor, or nearest neighbor interpolation. Okay, so nothing really fancy. And we saw the other day that this one has a problem. That is that the sampling this one. So let's say that I'm making a resizing by 3/7. So these scales are 3/7. Then the sampling, these yellow points, they have been shifted already. Okay, so they have been shifted to the nearest neighbor. So what we see is that there is a non-uniform pattern. So we have a pattern of taking a sample, then one node, taking another sample, one node, taking another sample, and two nodes. Okay, so that is a non-uniform pattern. No? And this creates aliasing. This is not so listen. Okay, so let's see if we can do anything better. So what is the equivalent in one dimension? So in one dimension, is I have a signal. That I have a signal. X and samples. Then I want to produce another signal. It's X prime. There is a relationship between the two. This photo. So we say that N is equal to S and prime. So S is the scaling factor. And then we are taking this sample here, this one from M prime of 1. Let's say that S is smaller than 1. Then we have to take this sample from this location. And this location, we don't have. So nearest neighbor is taking it from the nearest neighbor, that is this one. This is the nearest neighbor. So we will take this sample and put it there. This is nearest neighbor. Neighbor interpolation. What if I do something more intelligent? What if I join these 2 points by a line, and then I evaluate this line at this location? This would be more accurate. So this would be called linear interpolation. Linear interpolation because we are fitting a line. We are fitting a line, and then we are evaluating that line at the location we are interested in. Okay, this will be more accurate, and it is not very difficult to make it in one dimension. Now what we will do is the same, but now in 2 dimensions. So instead of taking, so what have we done here? We have taken all the neighbors around, just 2 neighbors in 1 dimension. We just have neighbors. And then we have fitted the line. So now we will take the 4 neighbors around. For 2 dimensions, we have 4 neighbors. Take these 4 neighbors around. Now, instead of fitting a line, the equivalent of a line in 2 dimensions is a plane. So we will fit a plane, and then we will evaluate the plane at this location. And so what is a line? So a line yeah. Line is always on the form. So let's be consistent with this direction. So line. This is confusing because X typically is for coordinates, but X is our signal. So this is A, and last B is the equation of this line. Isn't it? So this has been shifted. So that is a coordinate. So that is a coordinate. Coordinate. I multiply this coordinate by a vector, and then I'm adding a scalar. Okay, what is and that is my output, that is my signal. Okay, so what is the equivalent in 2 dimensions? So what is the equivalent in 2 dimensions? We will interpolate our image. Now we have 2 coordinates. So we have a coordinate that is X and Y. We have to multiply by something that is a vector. So then it has the same structure. There is a coefficient that goes in front of the coordinates. We have the coordinates, and then we have a scale. This is the equation of the plane. So it has exactly the same structure. And you can think of these. So what do you know of planes? So you know of planes. Let's say that our coordinates are x, y, equals 7. You know that a plane is typically represented in this way. So y plus z equal b. Okay, this is the equation of a plane that you know. But this, you can rewrite in this way. Wait, so you can say a divided by c, x plus b divided by c, y, z, it will be divided by c. And then we're saying, let's say, z is equal. Say that. So it's equal to minus a divided by c, x, divided by c, y, plus b divided by c. So now this has this same structure. This is a divided by c minus b divided by c x of y plus b. So it has the same structure as we had there. As this is our vector opposing from of the coordinates. These are our coordinates. Then this is our spectrum. And now if instead of saying C there, you say this is my image. This is my image. So now what you have is that your image is equal to that. Okay, so in general, our planes, this is an plane. You can take this idea to higher dimensions. So with this plane, because R has only 2 dimensions, but if you make R to be of any dimensions, then instead of a plane, you have an hyperplane. So actually, a line and a plane, they are both hyperplanes. So the line is an hyperplane in 1 dimension. The plane is an hyperplane in 2 dimensions. Okay, so let's do that. Then that is called bilinear interpolation. This is the other day, or this is the other day. Let's do the new thing, that is the bilinear interpolation. So the bilinear interpolation will, this is nearest neighbor interpolation. So nearest neighbor, you're simply replicating the values, nearby values. And now in bilinear interpolation, we'll make a smooth transition. And this smooth transition is because of this line or this plane. It's because of this line or this plane that you're fitting here. Okay, so there is a smooth transition between one value and the other. So we have smooth transition. Okay, so how to do that? So we are taking the 4 nearby values and we are fitting a plane. And we want to evaluate it there. Okay, so pick the plane and we evaluate it there. Okay, so let's see the results. We will go later to the equation. Okay, let's see for the moment that was nice. So let's say that take the image, we enlarge it, and this is the bilinear interpolation. So we are making it bigger. Now we have to interpolate the values in between. So this is nearest neighbor interpolation. And then this is a bilinear interpolation compared to this one. So if you try that big, much smoother. And this is nearest neighbor. Okay, so you see that the quality of this one depends on information, how many independent values we have. We have the same number of independent values, but this one is bad. This one is. Okay, so let's see. So this was our nearest neighbor interpolation tree. So we are taking the values from the yellow points. What about now with the bilinear interpolation? So when you do the scaling, when you take the coordinates, multiply by the scaling matrix, now you have these red points. So for these red points, you see that some of them are in the middle of 4 pixels. So we don't have the value there. That is why we have to interpolate. So, but now you see that if you focus only on the red, now it is uniform. So that you don't have this funny pattern of 1 pixel on, 1 pixel off, and then 2 off. But the distance between any two samples is always the same, always. Only that you don't have the values in the red points. You have to interpolate. But we already know how. So we have to fit the plane, and then we will evaluate the plane. Okay, so now if you look at the red grid, the distance between any two red points is always the same both directions in some way. Okay, so yeah, so this is zooming of that. Okay, so let's say that we want to take this value here. So we want to take that value. This is easy because we have the value at the pixel. Our red point is at the same location of one of our original pixels. So we simply copy. So that is not there. What about this one? Now our red value is not one. So we want to interpolate here. But the values that we have are these ones, the white ones. So we have to keep this plane. And the same there and so on. Okay, so you have to keep those. This is all the time here. So yeah, so we want to evaluate it here. That here in the slide it is called R fractional, C fractional. And we have it at these integer locations. So we will define, so it is a fraction. So let's put numbers first. So here, so n prime was 1. Then is 0.75. Okay, so this n equals 0.5. I can decompose into parts. One is the integer part is 0. And then the fractional part. This is called n fractional. So this is n, and this is delta n. So the fractional part is delta n. And the same will happen here. So let's say that I want to interpolate. At the location, I don't know, 100.3, comma, and then 50.75. This part here, will be the delta. Say that this is x, y. I is at most, C, x is almost, this is delta x, delta y, delta C, delta I. And the other part is the integer part. So the integer part will only tell us which is the coordinate that is close by. So the integer part will tell us which is the coordinate that is close by. And then we have the extra sheets that we go to the fractional part that we where we want to interpolate, that. Okay, so the suggestion is this one. Okay, so let's see. So this is the suggestion, and let's see if it makes sense. So what it says is, let's say that our point, our fractional point is here. So delta C, delta R are zero. So if delta C, delta R are zero, then 1 minus delta R, this is 1. 1 minus delta C, this is 1. So we have 1 times 1. Then we take the value from IRC. Okay, that's good. Delta R is 0, so all this product is 0. Delta C is 0, so all this product is 0. And also all this product is 0. So if delta R, delta C are 0, both of them are 0, then we are taking the value from IRC. That is what we should. Okay, so let's say that delta C is 1, but delta R is 0. Okay, so delta is 0. So delta C is 1. So this term is 0. This term is 0. Delta R is 0. So this term is 0. And the only one surviving is this one. What is this one? So it's delta C, but delta C is 1. 1 minus delta R, but delta R is 0. So this term is 1. So we have 1 times 1. And then I add R C plus 1. Okay, so this is seems to be correct. And this is a plane. If you may expand all the calculations, this is a plane in delta R, delta C. This is our X and Y, then we have a plane in X and Y. See that all of them are multiplied by something, like just stable. Okay, so it works as it should. So this is our plane. Somebody has solved it for us. It is a very simple plane. So it is simply to take into account which are the fractions and how far you are from each one of the four corners, and then somehow let's say that you are very close to this corner. You are very close to this corner this way. So this pixel should have higher weights than the rest because you are closer to it. That is actually what happens. If you put delta, delta C that are very small, this term is high, and all the other terms are relatively low. So this is our plane. This is the plane that we use for this interpolation. But this is everything based on the same thing I did. That was something over. Look at this. We have this plane. If you look in the x direction, what we have is a line. This is a line. And if you look in the y direction, what we have is also a line. So if you have a line in x and a line in y, that is why it's for bilinear interpolation. B. Okay, so we have this bilinear interpolation. We know how to do it. And then we can have bilinear interpolation with different scaling factors. So this scaling factor is defined here. So again, this -1 here, don't pay too much attention to it. It is just simply that you have to take into account, be careful with the voltage. The important part is R divided by prime. Well, let's here. So let's say that we have a couple of elements. Which one is C models right? Now we have limit I plus R prime C prime. So R prime all rows C prime follows. Now we take X and Y here. Way translating right. X and Y. So we have said X, Y, C, X, X, Y, zero, X prime, Y prime. What are these scaling? X is in this direction, so it has to do with C and C prime. So it will be C divided by C prime. Right. X is C prime. The corresponding is coordinate here. Coordinate there. Is coordinate here. This will be R divided by 5 prime. Okay, so the -1 is just the borders and the last function and so on. But this is not so important. Okay, so this is what you have. R divided by prime, C divided by C. And then that will give you function coordinates. So this multiplication will give you function coordinates. So this will be fraction. This will be fraction. And then you have this interpolation scheme with the delta C. So yeah, so here you have another example, but now with numbers. So let's say that we have these 4 corners, have these image values, but now they are vectors. So we have the R, D, and B components. And then we have a fraction that is 2/5 here, 2/5. Okay, so delta C are 2/5. Okay, so what are the values? So the value at this point is what we want to evaluate. I think that should be, this is an equal, I think. This is an equal. So the value at that point would be, so this point here is the first one. So it is, remember the formula. Formula is 1 minus delta R, 1 minus delta C. That means that you have to take this value and multiply it by this length. Multiply by this length. So we have this value here multiplied by this length next, and this length in one, but they are the same. And then we have to take this one. We have to multiply by the complement of this. It is always the length that is in the other form. So it will be two fields, and then 3, 1. And then this one, that is this one, yeah. So this one will be again times 3, 5. And this one is this one here. It is 2 fields. This is for rounding. Yeah, this is a 3. There is this relationship, and you can, if you want, you can call x, rounding of x. So you start at 0. So what is the rounding of 0? Is 0. Goes all the way down to 0.5. And then 1. 1, and stays 1 and 5. So this is the rounding. Now you do this the same, but now rounding down. Okay, this one. It turns out to be exactly the same. So why batteries? Because if you think in terms of code, this one is round. So that guy is calling the function, and this is more expensive. But this one here, this one is the x plus, and this is faster. So adding 0.5 is not too expensive, and a casting is not expensive either. It's called casting. So castings are not expensive, addition are not expensive, and calling a function is expensive. There is this trick. And then he has to use that. So you have to round, because in general, these multiplications will give you non-fractional fractional colors, and you don't have the fractional colors. So you add 0.5 to 3 components, and then you round down. Otherwise, we make a break of 10 minutes, and we continue. Actually, with this thing, also you can think of this in this way. So it is always a pixel value times the area of the opposite side. So this is this pixel value and the area of this side. It is this pixel value here, then this area, and then one on the opposite side. And this one is this pixel value, and then this area. One is this one, and so on. Okay, so now, sorry. So why restricting ourselves just for neighbors? So somehow for neighbors, if you think of it in this in terms of signals, so let's say that signal x of the then we have samples of this pigment, X of A. So now we have a value here in between. We wanted that value, and we were taking this line. So just taking two samples around give us information about what the function looks like in the neighborhood. But the function in the neighborhood, I know that if instead of taking just two samples, I take more samples. I take this one, this one, this one, this one. So the more samples I take, the more information I'm taking about the neighborhood. And what is that in terms of signal? So with the green ones, I'm able to estimate X. But with the blue ones, I'm also able to estimate the derivative. And the more samples, the more derivatives you are able to estimate. And that reminds you of something that is the Taylor expansion. That's it. So that reminds you X of T, X of some point that the derivative that point times the delta P. So this is the fractional part. So what we are doing actually with all this interpolation is just taking the Taylor expansion and taking more and more values of the Taylor expansion. So the more samples you take around, the more terms you will be able to estimate. So this one will allow you to estimate this one. This one. So bilinear or linear interpolation allows you to estimate that one. Then this will be quadratic approximation. Quadratic because the term that is left is quadratic. One cubic. The term that is left is cubic. So now let's go for the cubic. We will estimate, we will take more samples and we will be able to estimate the derivatives. We will able to estimate the first derivative because we are in a two-dimensional function in X, in Y, and X and Y. So here are the four values of bilinear interpolation. Now take all this neighborhood. And with all that neighborhood, we are able to estimate the derivative. So what is the derivative? Derivative. This derivative can estimate that derivative is this one. This one is taking these three values. They are shown here. So R plus 1C, R minus 1C. So have this value, and then we have the one before, the one at the value, and the one after. And this will be an estimate of this derivative. Yeah, and simplify this to this one. This is another estimate of the same derivative. These are two different ways of estimating the derivative. And then the same for, so this is for estimating the derivative in this direction. This is for estimating the derivative in this direction. Then we use this for the derivative in this direction, and you can estimate derivatives. So you can estimate what is the derivative here, what is the derivative here. Okay. the conforms. So, so here we have, for instance, this one, this direction, and this one. This one is in this direction. This one is this direction. And then you can estimate the derivative somewhere else. And now you can do this quickly. So when we have four organs, you will fit in a plane. Now with more information, now we can fit higher polynomials. So now the polynomials will be polynomials of degree 3. So, and in general, it has this form. So it has the intensity at each one of the locations, and then a polynomial that is evaluated next. It's evaluated in y. We had the same here with the bilinear interpolation. So with the bilinear interpolation, we have all the pixel values, and then a polynomial of degree 1 times a polynomial of degree 1. And this one was in x and in y. This one was in x. So here we have the same again. But now the polynomial is of degree 3. Now the polynomial is of degree 3. So it is this polynomial, it's defined in this way, and this polynomial is defined. So actually, have you heard of deep learning before? Deep learning, sure, neural network. Have you seen anything about neural networks in any form? The Redwood function. Have you seen the Redwood function? It's called the rectifier linear unit. The Redwood function is this one. In one of our papers, we will have the neural networks. This one here. When x is exactly this one. This x, if x is larger than 0, otherwise. It is this function. So it is the one is pure x. It's the red. You see, there are very nice connections between functions, interpolation, and neural network functions. Okay, so but we have the same structure that we've done before. So we have all the pixel values, and then the product of two polynomials. Before they were of degree 1, now they are of degree 3. And we have the fractional part. Fractional part with respect to the pixel that you're considering. So these are the fractional parts. And then this m and m are these indexes. So where these pixels are with respect to this one. So a bit more complicated, but the main idea is that it allows us to estimate derivatives, and these derivatives, they are connected. Taylor expansion. So we want to estimate derivatives because of the Taylor expansion. And the more information you take around, the more accurate your estimates will be. So this is the general basic. So let's say that we take this image and we expand it, with nearest neighbor interpolation, bilinear interpolation, cubic interpolation. Now you understand, nearest neighbor is stopping here. Nearest neighbor is just this one. This is bilinear, and this will be cubic. If we want to use the same names as we have in the slides. So this one is nearest neighbor. This one was Bilinear. This one. You see, Bilinear was using the fractionals in some linear way. Cubic actually is going terms. Okay, so this is original, and this is nearest neighbor. That is, this is original, this is nearest neighbor. Do you see some fun ones that is out here? So the linear interpolation is creating these ranges, these oscillations. What are those? Today, aliasing. And then Bilinear, and then it's BQE. In all of them, we are reducing and then expanding it again. Just to have the same size of the. And now in the opposite direction. So now we are making it bigger. This is the nearest neighbor. Bilinear. So the cubic is the best approximation because it has more terms in this Taylor expansion. It's up to big. Any question on interpolation? So actually, the lecture was about interpolation, was not about resizing. So resizing was just an excuse to introduce interpolation. So this operation here has a very simple structure. It was just an excuse to introduce interpolation. Okay, so now let's go for more complicated geometrical transformations. Generally, they are called working. So you have an image, you apply a working function, then you have to interpolate, and then you produce an output. So the idea is the same. This one here. So given any coordinate in the output, if you have to look for what is the coordinate in the input, that you have to go from. But now this transformation is much more complicated. So now it is a general application. So now we can fraction. It is a transformation on the output. Any general transform can be whatever. So when it can be whatever, it is called more. It can be whatever. And this is just a particular case. So let's say that we have this image, and it is an image where we know that buildings they are buildings. This tower and this train. So it is because of the perspective of the camera. So that's going to be correct for that. This is what we would like to have, where the towers are more stable. Okay, so let's try to find this transformation. So to do that, we will take some coordinates. Take coordinates again. This one's here. And let's look at this one. These are coordinates again. Now we want to make them straight. Look at this one. So this one is x. This is X in this direction, Y in this direction. We have some coordinate in X. And this one, because it should be straight, should also be the Y can change, but the X cannot. The X has to be 52. And it was not at the beginning. At the beginning, it was saying. So we have to move this coordinate here. And this one will stay. So this one will stay. And the same for all the others. So you define a transformation, and you want this transformation such that this coordinate doesn't move, this coordinate doesn't move, but these ones are moving. So you define a few points, and you define which are the correspondences. Now you know a way to move this coordinate. So let's say, okay, that is a transformation that I will say it is a matrix. So let's say that my coordinate original image will be some coordinate in the R prime. We call it K. So we take coordinates in the transform image, that is the one that is moved. We multiply by a matrix, and then we get the coordinate in the image. And now we have pairs. So we separately have eyes, and then we have this point goes to here, this point goes to here, this point goes to here. So we have R1 prime, R1, R2 prime, R2. Many pairs like. So you have an equation system that is R1 would be H R1 prime. For the pairs. And I can also rewrite this, which is very much like the same. R1 are vectors. Let's put sizes. So let's say that you have P points, P pairs. So this is the matrix. They have names for those matrices. 5 things. 5. What are the sizes of these things? Okay, so this is a matrix. Size. This is 2 times P. This is 2 times 2P. 2 times 2P. The equation is this one. So I want to solve, which is my answer. My answer is 8. So I want to solve for 8. I don't know the 8. I want to solve for 8. So if I want to solve for 8, I would say A is equal to Y X minus. Is that fine? So I multiply by X minus 1 on the left, the right, and then I get 1 8. That's correct. Sorry. Right. Multiplico por x menos 1 a la derecha, por la derecha, me queda eso. ¿Está bien? Sí. No. ¿Por qué no? Eso es. Sí, porque digo que está aquí. Porque X no es invertible. Para que una matriz sea invertible tiene que ser cuadrada. Esa no es cuadrada. So that means that we cannot find an H, a single H, that satisfies all these coordinates at the same time. So this is a square problem again. So what we want to find is the H minimizes the norm of y minus H. This is Lisa squares. The Lisa squares problem. And we know how to solve the Lisa squares problem. So now we know how to transform this into something that we can compute. So let's multiply by x transpose. Okay, so let's look at the sizes again. So this is 2 times 3, and this is 3 times 2. This is 2 times 3. This is 2 times 3 times 2. But then this is 2 times 2. This is 2 times 2. And now we can invert this. Say H is equal to y x to the power. Then x plus 4. This I can. And we know this H is the H star. I was looking in the list as well. So we have presented this part always as a tree, but we know that this tree is actually solving the least square problem. If you try all possible H matrices, and you compute for all possible H, is the distance between your predicted coordinates and the original coordinates. The one that minimizes all distance is this one. This is what you have in estimates. This H minus, yeah, and this is important thing. So H is going from where to where. So H, this definition is taking points from R, from the output, and yeah, moving there to the input. If I want to go in the opposite direction, if I want to go from here to there, I have to use H minus 1. It's another way of saying this implies that R J prime is H minus 1. But depends on which direction you're going. You have to use H, but you have to use H minus 1. Yeah, so here H minus 1 was used from K1. Same kind of equation that we had. Step on here. Okay, so let's see. So we have our coordinates, one thing, we have the coordinates in the other one. Compute H is 1. This is H1, then we can see the image. So we wanted to have these ones y and h times x is this thing. So they should be approximate. So you never satisfy all of them at the same time. Since this is a square concept. Squares. So you never satisfy this something that it is exactly zero. So you don't make hx be exactly y. In general, there are some particular cases where it can get that. But they should be approximately much closer than they were at the beginning. So that's the second point. Second point was 326. This was the original point. Now, it is not exactly 80, but it is much closer than it was. Okay, so now we do that. So this is how they were. This is where we want it to be. Blue is where we want it to be. Red is where it was. Then when we apply this, we needed something. Then make it straight. So goes a little bit into that the right direction, the classic. So let's see why. Yeah, this is a interesting relationship. That is okay. Age. So let's do the age. What is age? Age is it's not moving y. Y. Let's the shape of H, of course, that's what we were saying. X one. X y is equal to 0, 1, and then we have something like A and B, and then X prime y. It's X prime, so we need y prime. So y and y prime are the same, and X is not. This is what we wanted. It seems that what we wanted. So we have this powers here. The y was all the time the same. So the y of all these coordinates, the y doesn't change. Everything. This is the x that is changing. So this 80, we want to move it to 50. So it seems that age is behaving as it should. So age is changing x, but it is not changing y. Okay. And then this reasoning here, this reasoning is the following. Any matrix can be decomposed in this way. This is called the SVD decomposition of the matrix, like a singular value decomposition of the matrix. If you are familiar, SVD, you have ever seen it? Do you know what SVD is? Singular value decomposition. You know the eigenvalue decomposition. Okay, so the eigenvalue decomposition is this one. Have a matrix. Let's say matrix H. And then H. This is the eigenvalue decomposition. And the eigenvalues. So the eigenvalues. And that one. matrix some size n times n. And here this matrix is formed by vectors. Okay, so who are lambda? This is simple. This is a diagonal matrix with the eigenvalues, and then have these are eigen. Eigenvectors. Autovalores y autovectores, autovectors. So, which are these ones? These values are that 8 times 1 lambda 1 and so on. So if I take this vector multiplied by h, what I can get is the same vector multiplied by x squared. In general, that doesn't happen. If you take any vector multiplied by h, what you get is something different. But for eigenvalues and eigenvectors, so for eigenvectors, you get this relation. The same for all the others. So that is another decomposition. This is the eigenvalue decomposition. That is another decomposition. The eigenvalue decomposition is only valid for square matrices. For non-square matrices, you have the SVD decomposition. SVD decomposition is this one. And is U S B transpose. And S is again one. Can have zeros. For some of these, I get singular values of 0. And this is for non-square matrices. Okay, non-square and square matrices. So for both. So we can decompose our matrix in an SVD. And this SVD decomposition has a property that U and B, they are unitary. U and B are unitary. That's it. So a matrix U is unitary if U times U transpose is identity, and U transpose is identity. And you may not remember, but this is the definition of the rotation. This is a rotation. Look at, remember this matrix. Have you seen this matrix before? Yeah. So it is the equation of a rotation. So if I take any R, it's just a rotation by theta degrees. So this is a matrix that includes this one. And in general, so this is the 2D rotation, but in general, any matrix that fulfills this, it is a rotation. So U and B are rotations. So what it is saying is that there is a rotation. It's another rotation. And there is a scaling. This is the scaling we just showed in the last lecture. It's a matrix of the section. So any matrix, any transformation, any linear transformation in this way can be decomposed into a rotation, then a scaling, and then another rotation. And in this particular case, for this one, it is a rotation counter, so clockwise rotation of 90 degrees. Then this scaling, and then counter clock rotation of minus 90 degrees. So let's do that. So we first rotate by this. Now we scale. Now we turn back. And this is already rotation of this point. For any rotation h, whatever that is, it is always the rotation, then the scaling, and then the counter rotation. Always. So this generates something. Okay, so it says how not to do it. So all this theory is very fine, but we didn't succeed. We didn't make our estimate. Why? Because the tower is, so this perspective is a 3D transformation. Perspective is something that happens when you go from 3D to 2D. And this transformation here, it goes from 2D to 2D. So I find our perspective. This is 2D. This is 2D. This is 2D. And perspective is something that happens when you go from 3D, but we don't know yet how to go. Okay, so let's see. So we have to figure out a way to transform this problem into a 3D problem. Okay, so let's say that we expand our coordinates in this way. We expand our coordinates such that we added one at the end. And then now it is 3D. This H will be also 3D. And then it will produce something that is a 3D coordinate. This is 3 times 1. This one is 3 times 3. And then this will be 3 times 3 times 1. Okay, so this expansion by 1 is a 3. It's called the homogeneous coordinates. What are these homogeneous coordinates? So let's say that I have a coordinate x and y. I will transform this. This is a 2D one. I will transform it, and you call it R. We're transforming it into a homogeneous. And the homogeneous will be AX, AY, A. So R, this means that, and this is 3D. This transformation is not unique. So for any case, so I can associate this to the coordinate. I can associate any homogeneous coordinate by changing k. So if k is equal to 1, I will have a. This is equivalent. Is but well, this y. So in general, when you have an homogeneous coordinate, responding coordinate is, I can say that this is a c. So this would be a divided by c by c. B divided by c. And this is so given an ABC coordinate, homogeneous coordinate, the corresponding point in 2D is A divided by C, B divided by C. So these two homogeneous coordinates, they represent the same point. Okay, so we have transformed, we have really step more. So we have transformed our 2D problem into a 3D problem. Now we use these homogeneous coordinates. So we have the xy, now the m5 Now this is 3D. We have to look for the H matrix that is also 3D, and it will produce an homogeneous coordinate. And this homogeneous coordinate is corresponding to a point in the real space. That is this one. Given the output of the transformation, I will have still to translate it into the coordinate that I understand. Any question? So what we have said is, I can, given a 2D coordinate, I can associate a homogeneous coordinate by choosing any k. I can choose k equal 1, I can choose k equal 2. I can choose k equal whatever, and they all represent the same point, that is this one. But there is not a unique homogeneous coordinate associated to a given point. There are infinitely many. So next day, we will look for H. We will look for what is the transformation. Ahora